everyone, and welcome to linear programming. We are going to talk about how to write a system of equations for a linear programming problem, and then how to maximize or find the maximum values within that system for the given application. So really just need to look at an example and kind of work through that, and maybe we'll look through a couple here as we go. All right, so in the following example says, a carpentry shop makes dinner tables and coffee tables. Each week the shop must complete at least 9 dinner tables and 13 coffee tables to be shipped to furniture stores. The shop can produce at most 30 dinner tables and coffee tables combined each week. If the shop sells dinner tables for $120 and coffee tables for $150, how many of each item should be produced for a maximum weekly income? And then what is that maximum weekly income? All right, so let's take it a piece at a time. So ultimately we're asked how many of each item should be produced. So those are the things that we do not know, and so it does help to start by defining our variables. Even though sometimes it's convenient to make variables that are the letters that you like, I'm going to go ahead and stick with x and y, keep them straight on our axes. That might make things easier for us all. So I'm going to go usually in order that what they're presented in the problem. So x, I'm going to make the number of dinner tables, and y to be the number of coffee tables. Let's go sentence by sentence to see what information we can turn into some equations or inequalities for ourselves. So each week the shop must complete at least 9 dinner tables. So the dinner tables must be at least 9. So that means x must be greater than or equal to 9. That's one inequality. Another says, it also says, in at least 13 coffee tables. So y must be greater than or equal to 13. Good, 2 so far, and those will be nice and easy to graph. It continues saying the shop can produce at most 30 dinner tables and coffee tables combined. Okay, dinner tables is x, coffee tables is y, so dinner tables and coffee tables combined would be x plus y, and it says they can produce at most 30. So can't produce 30, something less, or can produce 30, but nothing more than 30, so less than or equal to 30. Great, so we have 3 inequalities that we're going to graph. In theory, we could also talk about, since we can't produce negative numbers of either of these, that x must be greater than or equal to 0 and y must be greater than or equal to 0. For this example, these are really kind of unnecessary because we already know that x and y are greater than 9 and 13 respectively. So we don't really need these because we've got more precise inequalities up above. Okay, so we've got to go ahead and begin to graph this, and you're like, wait, what about all this other information in the problem? Well, let's come back to that in a second. It says if the shop sells them for this price and coffee tables for that much, how much income will be earned? We're going to do that in the second half of this problem when we're looking at to maximize the profit. But first, let's just graph how many coffee tables it's possible for them to produce. That's what we're looking at first. Then we'll talk about which amounts should they make. So if we look at our graph space, just eyeballing it, I can tell clearly that I don't have enough space to count up to 30. And why am I thinking about 30? I'm thinking about how I would graph this inequality here. And if I graph this using the intercept method, I know that if I put 0 in for x, y would be 30. And if I put 0 in for y, x would be 30. And really, I want to make sure that I get both intercepts of this graph in my coordinate plane so that I can see all possible values that might exist. So I'm not going to be able to count by ones, so let's count by twos, which really means, because I'm lazy, I'm going to count every other line as 4. So that's 4, 8, so I really mean I'm still counting by 2, 12, 16, 20, 24, 28, 32. And just as a reminder, I'm going to label that this is our dinner tables down here, because that's our x, and we're going to put coffee tables over here. Let's keep the same scale going here, so that's 4, 8, 12, 16, 20, 24, 28, and 32. Great. So as we said, for this inequality, we've got intercepts at 30 for both. So that's a point right here and a point right there. So we'll go ahead and connect them with a line. We have to think about, do we want a solid or a dashed line? And since we have a less than or equal to, we want a solid line. Please get a ruler because that will make your work so much neater than my work. I will do my best without a ruler here on my tablet. You should be going diagonally through these lines, through the grid lines. Being accurate here is highly important, so please get a ruler. Yours will look even better than mine, but that's the line that we should have for x plus y is less than or equal to 30. Now, x is greater than or equal to 9. That's a vertical line, and the unmarked line here on our x-axis is 10, so 9 is going to be here. And again, it is a solid line. I'm going to try to stay right in the middle there. I'm not doing the best job, but we all know that that's 9 through and through, and that will keep going up. And then y is greater than or equal to 13 is going to be a horizontal line. Here's 12. This line would be 14, so 13 is here. Great. All right, so we have our 3 lines, and they're all solid lines. Let's consider which way we should be shading for each of them. So for our diagonal line, if we think about the point 0, 0, the origin, would that be true? Well, 0, 0, yes. 0 plus 0 would be less than 30. So for the diagonal line, we're going to be shading towards the origin, so this way. For our vertical line, we're looking for points that are bigger than 9, so that's going to be towards the right. And for our y equals line, our horizontal line, we're going to be going up because we're looking for greater than. So hopefully you've kind of identified that we are looking in this little triangle here. Great. Inside of here, any point that exists would be all the possible numbers of coffee tables and dinner tables that the carpentry shop could produce. So because it's the possible answers to our problem, we call this, actually, you'd think we call it the possible region, but let's pick a fancier word than possible and call it the feasible region. So that is the feasible region right here. The region where all the possible combinations occur. Now, if we're trying to figure out the maximum income, you might think, oh my goodness, do we have to try out every single combination that exists in this region? That's still a lot of different combinations. Well, luckily, we won't have to try every single one of them. There is a principle called the corner point principle, and that states that the optimum set of points in the feasible region occurs at a corner, or in other words, intersection point of the region. So our feasible region is a triangle. So we have 3 points of intersection. Depending on what kind of shape you formed here as your feasible region, you might have more. All right, so this point down here was the intersection of the lines x equals 9 and y equals 13. So that's clearly the point 9, 13. This point over here, it is on the line y equals 13. So that's definitely going to be our y coordinate, 13. And hopefully you can see that it looks like 17 from our x-axis. But if you're in doubt, you can think about the other equation. It was x plus y is less than or equal to 30. So if y is 13, x must be 17 to give us 30. And same thing here. We know its x value is 9 because it's on the line x equals 9. And so if x is 9, y must be 21. And it does appear to be that from our graph. So those 3 points, one of them will be the maximum income from making coffee tables and dinner tables. So we just need to test each of those to see which one's the best. Well, what do you mean test them? How do we even figure out how much income they would make from one of those? Well, now we need to reconsider the information in the problem. So it says dinner tables sell for 120 and coffee tables sell for 150. Dinner tables 120, coffee tables 150. That gives us our income. So we're going to make a third equation for the thing we want to maximize or sometimes minimize. That's why in the definition I put the optimum, because maybe we want to minimize something or maximize something. So we want to optimize something. So anyways, this time we want to maximize income. So I'm going to make I for income, and that's equal to, gotta check my numbers again, 120 times the number of coffee tables. And we said dinner tables. 120 times the number of dinner tables, which is x, plus 150 times the number of coffee tables. So whatever number of dinner tables and coffee tables we make, we multiply by 120 and 150 respectively, and we will get that maximum, that income. So let's test them out, see which one gives us the most. So if we picked 9 and 21, 9 plus 150 times 21, that's going to give us 1,080 plus 3,150 for a total income of 4,230. Okay, great. But is that the most income? We don't know. Let's test another point. So let's do the 9 and 13. I equals 120 times 9 plus 150 times 13. Some of you are like, well, clearly that's not going to be the most. If we want to be extra diligent, we could, make sure by testing it out. But you should be able to recognize that because we are just straight up making less of the coffee tables, that clearly we're not going to have our maximum profit. So that's only $1,950 added to 10,080 gives us 3,030. So that's less. But what about our third point? This one might be at least worth considering. All right, so 120 times 17 plus 150 times 13. Great. Okay, so 120 times 17 gives us 2,040. 150 times 13, we already did that, is 1,950. We add those together, and we get 3,990. So we have three different incomes from the amount of tables that we make. So the best income was this 4,230 from making 9 dinner tables and 21 coffee tables. So that's our answer. Let's put it in a nice sentence here. The maximum income is $4,230 from making 9 dinner tables and 21 coffee tables. So you can see why I only put one problem on this page, because there's a lot that goes into it. We first started by defining our variables, writing a system of inequalities, graphing the system of inequalities, finding the feasible region, the region where there's possibilities to be met all these conditions. We use the corner point principle to recognize that one of these three, in this case corner points, will be the maximum for our situation. And then we tested them in our equation for income and found out 3 different incomes, and so the maximum income came from this scenario, and so then we lastly finished by answering the question. That is a linear programming problem, and we will do a couple more examples, but take them one step at a time. And